Hello, welcome to our class on circle geometry. Okay, so let's first define a circle. A circle is the locus of all points equidistant from a fixed point. The fixed point is the center of the circle. So we have a circle. This is the center of the circle. All points, the locus of all points having equal distance from this fixed point called the center. Equidistant, they all have equal distance. So the locus of all points equidistant from a fixed point is called a circle, and that fixed point is the center of the circle. So sometimes center of the circle can be denoted by C. Sometimes we can denote it using O. So here we have the circle shown. Okay, so let's have some definitions with respect to circle. So we have what is called chord. Here is the center of the circle. From the center to the circumference, that's called radius. A line that passes through the center touches 2 points on the circumference, that's called diameter. So a chord is a straight line that touches 2 points on the circumference of the circle. So that's the definition of chord. So if we decide to have a circle, so here we have chord, we could draw several chords. Just ensure that the straight line touches the 2 points on the circumference of the circle and ensure that it doesn't pass through the center of the circle. See, the straight line touches 2 points on the circumference of the circle and it doesn't pass through the center. So all what we have here are called chords. So they are all chords of the circle. So a diameter is basically a chord that passes through the center of the circle. So the moment the chord passes through the center of the circle, it becomes diameter. Fundamentally, the diameter divides the circle into two equal halves. So diameter divides the circle into two equal halves. So once you have a straight line that passes through the center of the circle, touches 2 points on the circumference, the line is called a diameter. And it divides the circle into two equal halves. So here is a semicircle, and here is also another semicircle. The diameter can be shown in several ways. So there is diameter, and it divides the circle into two equal halves. So radius is the distance from the center of the circle to any point on the circumference. So the distance from the center of the circle to any point on the circumference is called the radius. So let's have radius. So observe that we take the distance from the center to touch any point on the circumference. So this is radius. Center to any point on the circumference, this is radius. Center to any point on the circumference, this is also radius. Distance from the center to any point on the circumference. So we can say that if the whole length is diameter d, and we have from this point to this point radius, from here to here is also radius, that means radius plus radius equals to diameter. So diameter is basically 2 radius. That's the relationship between diameter and radius. Diameter is twice the radius. Let's talk about circumference. Circumference is just the same concept with perimeter. The total distance around the circle is called the circumference. So if you have a circle and we have the center of the circle. So the distance around the circle is called the circumference of the circle. Distance around the circle is called the circumference of the circle. Let's define arc. Arc. An arc is a part of a circle. So an arc is a part of a circle. So let's say we have a circle. We have the center of the circle. Now this part of the circle is an arc. So this is an arc. This part of the circle is also an arc. Now let's explain more theorems. If you have a typical circle like this, and here we have the center of the circle. Now let's not forget that we said this is a chord. Now, what will be the effect of this chord? We can have two arcs. Here, this is an arc. Since we said an arc is a part of a circle, this is also an arc. Now, the bigger arc is called the major arc, while the smaller arc is called the minor arc. Now, another effect of a chord. Now, let's say this is a chord. Here's the center of the circle. Now, the chord can also divide the circle into two parts. Now, the part here will consist of the arc and the chord. Now, the part here is called a smaller part, that's minor segment. So the chord divides the circle into two segments, minor segments. Then the bigger part that consists of the chord with a bigger arc is called the major segment. So that means we can say the segment usually contains the chord with an arc. So this is the major segment. Now let's show the segment properly. This is what we mean. Something like this: chord, arc, minor segment, chord, then a bigger arc, major segment. So that's what we have there. Now we'll be learning some circle geometry theorems. So we call them circle theorems. We'll be taking some circle theorems. Theorem 1. A line drawn from the center of a circle perpendicular to a chord bisects the chord. A line drawn from the center of a circle perpendicular to a chord must bisect the chord. So let's say we have a chord and we draw a line from the center of the circle to meet the chord at that point. The line drawn from the center of the circle to meet that chord, first it must be perpendicular to that chord. That is, it must make angle 90 degrees to that chord, and also it will divide the chord into two equal halves, and that's a bisector. That's theorem 1. Let us proceed. Theorem 2. Chords that have the same distance from the center of the circle are of the same length. So let's say this is center of the circle. We have chords AB and chords CD. The two chords have the same distance from the center of the circle, so they are equidistant from the center of the circle. So we have, let's say center of the circle is O. ON is equal to ON. OM is equal to ON. The two chords have the same distance from the center of the circle. Hence, the two chords must also be of the same length. Then we can say AB equals to CD. Then we can say AB equals to A to B, then D to C. So that's the concept of theorem 2. Let's move to theorem 3. Theorem 3 states that the angle which an arc of a circle subtends at the center is twice the angle the same arc subtends at the circumference. So I prefer to shorten this theorem as angle at center is twice angle at circumference. So this short form is fine. So this is the center of the circle. So let angle at center, let angle at the circumference be x. Then angle at center is 2x. The angle subtended by this chord, the angle subtended by this arc at the center, the same arc subtend angle at circumference. Now this arc subtend a particular angle at the center. Let's call it M. The same arc subtend a particular angle at the circumference. The same arc subtend a particular angle at the circumference. Let's call that N. So we can use the concept of angle at center. It's twice angle at circumference. Angle at center is M is equals to 2 times the one at circumference. So basically, I can give an explanation like that looks like this. The angle here in this direction. The angle here also in this direction. That's another way to quite understand it. The angle here in this direction, the angle here in this direction. The angle facing towards the same direction. So the arc here makes an angle at the center. The same arc makes an angle at the circumference. So let's say the angle at center, let's put P there. The one at circumference, let's put Q there. So we said angle at center is twice angle at circumference. Angle at center is equals to 2 times angle at circumference. So the angle at center, look at it, down, circumference down. Circumference is the one that touches the body of the circle. So angle at center, that's P, equals to 2 times the one at circumference. So P equals to 2 times Q. Let us move to theorem 4. Theorem 4, angle in a semicircle is right angle. So one important thing about theorem 4 is that we must have a semicircle, and for us to have a semicircle, we must have a diameter there. So angle in a semicircle is right angle. So we must see diameters in each of them. So because diameter actually divides the circle into 2 semicircles. Now, how do we trace angle in a semicircle is right angle? We'll trace from the extreme endpoint of the diameters. From the extreme endpoint of the diameters. From the extreme endpoint of the diameters. Okay? Now, from the extreme endpoint of the diameter, we trace to the circumference. Any part on the circumference here, any part. Let's put it here. Trace the other extreme point. Trace the other extreme endpoint of the diameter. Trace the other extreme endpoint of the diameter. Trace it to the circumference. The angle that will be formed here will be angle 90 degrees. This is the symbol for 90 degrees, and that's right angle. Let's trace from the extreme endpoint of the diameter to any point on this circumference. Trace the extreme endpoint of the diameter to the endpoint of the circumference. The angle that will be formed there will be 90 degrees. And that's what we call right angle. So this is the mathematical symbol for angle 90 degrees. And that's the theorem which says angle in a semicircle is right angle. So let's show it here. So that's 90 degrees. So let's write 90 in full. Trace the extreme endpoint of the diameter. Trace it to any point on the circumference. Trace to any point on the circumference. We still have 90 degrees. And that's the theorem. Let's proceed to theorem 5. Theorem 5 says angles in the same segment are equal. Angles in the same segment are equal. Remember that a chord divides a circle into 2 segments. So all angles going towards the same segment are equal. So let's trace it from the extreme endpoint of the chord going towards the major segment. going towards the major segment from the two extreme endpoints of the chord, from one extreme endpoint of the chord, the other extreme endpoint of the chord. Make sure it touches the circumference. All the angles here will be the same. So let's say if this is 30, for instance, this will also be 30, and this will also be 30. Still on the concept of angles in the same segment are equal. If this is a chord, let's trace from the extreme endpoints of the chord towards the same segment. The angle formed there, let's assume is 60 degrees, for instance. It will be the same as the angle formed towards the same segment from the extreme endpoints of the chord. There will also be 60 degrees. And that's the idea of angles in the same segment. Let's say we still have a chord. So all the angles from the extreme endpoints of the chord, draw a line, touch the circumference. From one extreme end, from the other extreme end, touch the circumference. From one extreme end, touch the circumference. From the other extreme end, touch the circumference. So the angles will be the same. We call them angles in the same segment. So if this is M and this is N, we say angle M equals to angle N, angles in the same segment. They are all going towards the major segment. And that's the idea of angles in the same segment are equal. And that's theorem 5. Let us proceed to theorem 6. Theorem 6 says that opposite angles of a cyclic quadrilateral are supplementary. Opposite angles of a cyclic quadrilateral are supplementary. So we all know that a quadrilateral is a four-sided polygon. A quadrilateral is a four-sided polygon. Now, each of what we have here are all cyclic quadrilaterals. As you can see, the four corner points must touch the circumference of the circle before you can call them cyclic quadrilaterals. The four corner points touches the circumference of the circle. So they are all cyclic quadrilaterals. So opposite angles must add up to 180 degrees. The word supplementary means add up to 180 degrees. So here is M and this is N, opposite. So we can say M plus N must add up to 180 degrees. We have P here and we have Q here, so we say P plus Q must also add up to 180 degrees. Opposite angles. Here this is A, for instance, and this is B. A plus B must add up to 180 degrees. Here if this is C and this is D, for instance, C plus D must also add up to 180 degrees. Opposite angles of cyclic quadrilateral. Another cyclic quadrilateral, this is X and this is Y. X plus Y must add up to 180 degrees. Opposite angles add up to 180 degrees, provided they are cyclic quadrilaterals. R and T, for instance, we say R plus T must also add up to 180 degrees. Opposite angles of cyclic quadrilateral. They are supplementary. Now, but let's not forget one very important theorem about quadrilaterals. If you sum up all the angles inside, it will always be 360, irrespective whether it's cyclic quadrilateral or not. So, for instance, we could sum up P and QN to give 180 degrees. Remember that from polygons, sum of angles inside a quadrilateral will always give 360 degrees, whether it is cyclic quadrilateral or not. So, considering this shape, we can say P plus M plus Q plus N equals to 360 degrees. So that's just a theorem for sum of angles inside a quadrilateral. Sum of interior angles of a quadrilateral. Now let's just proceed with that. Now let's have still the concept we're explaining. Let's say this is the center of the circle. Remember that a quadrilateral is a four-sided plane shape. Now, here we also have a four-sided plane shape. 1, 2, 3, 4. Now, but this is a non-cyclic quadrilateral. So opposite angles will not add up to 180 degrees. Non-cyclic quadrilateral, look at the four corner points. 1, 2, 3. Only 3 touches the circumference of the circle. So the last one does not touch the circumference of the circle. So it is non-cyclic quadrilateral. Hence, opposite angles will not add up to 180 degrees. Let's move to theorem 7. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Also, for this theorem to hold, it must be a cyclic quadrilateral. So let's have a typical cyclic quadrilateral, so that we have one of the angles to fall outside, and that will serve as the exterior angle. Let's call it A, and let's call this B. So the exterior angle is A. It will be equal to the interior but opposite it. So A equals to B. That's theorem 7. Moving on, theorem 8. A tangent to a circle is usually perpendicular to the radius of the circle. So one thing we need to take note is that a tangent is a straight line. So that we can understand that theorem, a tangent is a straight line that touches a circle externally at only one point. So a tangent is a straight line that touches a circle externally at only one point. So let's have tangent. So this is tangent. Touches the circle outside externally at only one point. Then we can have radius. distance from the center to any point on the circumference. So radius and tangent makes angle 90 degrees to each other. So the tangent to a circle is usually perpendicular to the radius of the circle. That's theorem 8. That's a tangent. This radius of the circle. They make angle 90 degrees with each other. So let's move on to theorem 9. Two tangents drawn to a circle from an external point. Are equal in length and subtends equal angles at the center of the circle. So we have two tangents drawn from a given external point to a circle. The tangents are equal in length and they also subtend equal angles at the center of the circle. Okay. So here we have the circle. This is the center of the circle. The tangent drawn from this external point. So let's say this is T, A, B. First, the two tangents are equal in length. TA must be equal to TB according to the theorem. And they must subtend equal angles at the center of the circle. So let's have radius. So they must subtend equal angle at the center of the circle. Let's join. Let's say this is O, so let's join OT. So subtending equal angles at the center of the circle simply means the angle here and the angle here will be the same. So we can say angle TOA is equals to angle TOB. Okay, the two tangents are equal in length, one, and they also subtend equal angles at the center of the circle. That's what the theorem talks about. But don't forget that OA is radius. So we can say OA is equal to OB, distance from the center of the circle to any point on the circumference. So that's radii. Now, angle TAO also is equal to angle TBO. Angle between a tangent and radius is 90. So tangent to a circle and radius makes angle 90 degrees with each other. So we say tangent perpendicular to radius, tangent perpendicular to radius. Okay, so a tangent to a circle usually make angle 90 degrees with the radius. So in conclusion, the two triangles are the same. Triangle OAT is fundamentally the same as triangle OBT. So we can draw the conclusion that triangle OAT is equal to triangle OBT. They are congruent triangles since they have same side lengths and same angles. That's congruency. Let us move on to some special cases. But before that, let's talk about Theorem 10, angle in alternate segments. Let's talk about Theorem 10, angle in alternate segments. Angle between a tangent and a chord is equal to angle in alternate segments. Angle between a tangent and a chord is equal to angle in alternate segments. So let us try to explain that theorem. We need to have a tangent and we also need to have a chord. So angle between a tangent and a chord. So this is chord. So let's say the angle here. Angle between a tangent and a chord. Now the angle is located in this part of the segment. Then this part will be the alternate segment. Let's call it X. So X will serve as the alternate segment. So angle between tangent and chord, let's call it angle theta. Angle between tangent and chord equals to angle in alternate segment. How do we trace it? Trace to the alternate segment, that's X. Trace from the extreme end point of the chord, let it touch the circumference of the circle, let it touch the circumference of the circle. Then automatically this place will be angle theta. Let's explain further. Angle between a tangent and a chord is equal to angle in alternate segments. So let's say this is a tangent. Let's say this is a chord. And the angle is located here. Let's call it angle alpha. So if the angle is located here, in this part, then the other part will be the alternate segment. So I'll still call it X. So X here is the alternate segment, that part. So angle between a tangent, look at it, this is the tangent, and this chord is equal to angle in alternate segment. So we trace from the extreme endpoint of the chord to the alternate segment and we trace something that looks like a triangle. But ensure it touches the circumference of the circle. So automatically the angle here is angle alpha. So that's the idea of angle in alternate segments. Now we can now proceed with the special ones. Let us talk about what we mean by secant. A secant is a straight line that cuts a circle at two distinct points. So we need to have a diagram to understand what we mean by secant. So it must cut it at two distinct points on the circumference. So let's say it cut it at A and B. In that way, that's secant. This is secant. Must cut it at two distinct points along the circumference. So that's secant. Let's talk about intersection of tangent and secant. Intersection of tangent and secant. So let's say we have a tangent here, then we have a secant. There's a meeting point. So let's say this is T. Let's say this is A, B, C. Formula that connects TA square equals to TB times TC. So let's take note of the formula. Distance from TA, we square it, equals to distance from T to B multiplied by distance from T to C. That's intersection of tangent and secant. Now let's talk about intersection of two secants. Intersection of two secants. We can generate a formula which is TA times TB equals to TC times TD. So distance from T to A times T to B equals to T to C times T to D. That's intersection of two secants. Let's talk about intersection of chords. Intersection of chords. So let's say we have a chord like this, another one like this. let's say A, B, C, D, E. So the formula AE times EC AE, A to E times E to C equals to B to E times E to D. A to E, then we move from E to C equals B to E times E to D. Thank you for listening. We have come to the end of this section. In our next class, we'll look at questions from examination, past questions, and model examples. Thank you for listening. I'll see you next time. Bye.